Welcome to my first video about inductors. So, what's an inductor? Generally speaking, an inductor is a device that temporarily stores energy in the form of a magnetic field. Inductors are usually just coils of wire, and one of the basic properties of electromagnetism is that when you have current flowing through a wire, you'll create a small magnetic field around it. So if you coil up a lot of wire, you'll get a stronger magnetic field. When current first starts to flow through the coil, a magnetic field starts to expand, then stabilizes, and then you've got some energy stored in the magnetic field. When current stops flowing, the magnetic field starts to collapse, and the magnetic energy gets turned back into electrical energy. So they're kind of like a temporary storage area for energy. You know how capacitors store energy in the form of a static charge and resist sudden changes in voltage? Well, inductors are very similar. They store energy in the form of a magnetic field and resist sudden changes in current. And if you only learn one thing from this video, remember, the current in an inductor cannot instantly change. It always lags by a certain amount of time. Now let me give you an example. Normally when you connect a voltage source to a load resistor, the current will be given by Ohm's law. In this case, 10 volts divided by 20 ohms gives you half an amp. And for this demo, I'm going to be using a 50% duty cycle square wave, so half the time you'll get 0.5 amps flowing, and half the time there'll be no current flowing. Okay, so here's the 1 kHz input square wave. And here's the current waveform, also perfectly square. Now watch what happens when I add a 5 mH inductor in series with the circuit. All of a sudden the square wave isn't so square anymore. There's a little bit of lag in the current. And this is because it takes a certain amount of time to store and release the energy in an inductor. Now let's try that again with a higher input frequency of 10 kHz. Now it's even more obvious that the inductor is impeding the sudden changes in current. This happens more and more as I raise the frequency of the input wave. At 100 kHz, there is no square wave anymore. It takes a longer time to store and release the energy in the inductor than the time it takes for the input wave to switch from high to low. So in this situation, the inductor is starting to average out the current over time. And this is very useful. It forms the basis of LC low-pass filters, which I'll cover in another video. But just to give you a quick example, if I add a 1000 microfarad capacitor just after the inductor here, I get a very clean DC output from a square wave input. And this is what good power supplies use to smooth out voltage. And to prove to you that all this happens because of expanding and collapsing magnetic fields, I'm going to feed a square wave into this unshielded inductor here. And I'm going to use another inductor as a magnetic probe, so I can view any magnetic field changes on the oscilloscope. On top I have the input wave, and on the bottom you can see the magnetic field that I'm picking up as I get closer to the inductor. Finally, inductors have almost no effect on DC. They're basically just pieces of wire with a resistance of a few milliohms. Alright, that's the basics of how an inductor works. Now, I've got a couple more videos with more info on them and some practical examples.